In this video, we're going to review the ideas of commuting and non-commuting operators. And this whole idea for quantum mechanics is trying to address the question of which observables can we know simultaneously. So in quantum mechanics, unlike classical mechanics, we can't actually know everything about an object at once. And that's because these objects aren't, particles. They are these quantum mechanical wave particles. So they don't act like particles do, and they exist in this quantum superposition. So, when we operate on a wave function, there are two options. First, if that wave function is an eigenfunction of the operator, we return that eigenfunction multiplied by a constant. And that's going to give us one certain value that we can know. However, if the wave function is not an eigenfunction of the operator, we're going to take that superposition wave function, we can say, and force it to become an eigenfunction of the operator. And that fundamentally changes how the wave works. So then if we try to make another operator, try to measure another value, we can't go back to the original state. So say we try to measure the momentum, we get some answer, but now we've changed the wave function. And so we can't go and measure the original position because we've changed it when we made that momentum operation. So we can use, mathematically, we can use this idea of operators and if they commute or not to know whether or not our operators will commute. And then if our operators commute, we'll know that we could know both of those, the observables that go along with them simultaneously. So to do that, we need to ensure that our function is essentially an eigenfunction of both operators. And so I've set up a scheme here where you can see we have a function e to the 2x, and we have two operators, operator a being one derivative, and then operator b being pi multiplied by two derivatives. And since our function is e to the x, it's actually an eigenfunction of both of these operators. So that means that our operators here should commute. We should be able to know both a and b measurables simultaneously. And we can do that by simply operating on our function with both of these operators. So if I operate on f with operator a, I'm taking one derivative. That's going to give me 2e to the 2x, which is simply 2 times my original function. And if I operate it on b, that's going to give me 4 pi times e to the 2x, which is 4 pi times my original function. And so all I've done in this situation is multiply by a constant. And so that's actually not going to affect successive operations. So then if I went here and took, operated on my function with b after I've already operated on it with a, I'm simply going to get 2 times 4 pi times f of x, which is 8 pi times f of x, because I'm just, again, taking one derivative of e to the 2x, and then that constant just hangs out and doesn't do anything. And if I do the reverse order, so if I operate on it first with b and then with a, I'm going to get the exact same thing, 8 pi times my original function, e to the 2x. So here, the fact that these two are the same means that these operators commute. The order I use them doesn't matter, and I can know both my hypothetical a and b values, my 2 and my 4 pi, for whatever observables these correspond to, simultaneously. So in the quantum mechanical math, the way that we write this out is we need this term here, this b a f of x. I'm going to copy that. So b a f of x minus a b f of x should equal 0. And we can see how that works out here in the example problem. But in any sort of arbitrary problem, that needs to be true as well. So if the difference between these is equal to 0, that means that these operators commute. And we can see how that works in the above example. And so the way we can write this, and I think the way I've actually ordered it here, it would be b then a. So taking this and is equal to 0. So it's just a shorthand way of writing the same thing I wrote over here. And this b comma a or a comma b is the commutator. So if the commutator is 0, our operators commute. We can know both of their observables simultaneously. If the commutator is not 0, the operators don't commute, and we cannot know both of their observables simultaneously. So let's use an actual example to show how we do this. So of course the example we're going to do is momentum and position. So the position operator is simply x, the momentum operator is I h bar, and then one derivative with respect to x. So if we were to go and evaluate the commutator, so maybe we want to know the commutator p sub x and then x, and what is that equal to? So to solve this, we need to apply it to an arbitrary function. So we can start we'll take our p sub x, and we'll take that on an arbitrary function f of x. So that gets us simply IH bar and then times one derivative of f with respect to x. Now we're going to evaluate with the next operator, so x. So we're going to use x on our function after we've already measured the momentum. And that's going to give us minus IH bar x df dx. So to check if the operators commute, we need to do this in the reverse direction and see if we get the same thing. So let's do that. So let's take x and then f of x, and that's simply going to be x times f of x. And then we can operate on that with the position or the momentum operator. So p after we've already done x. And here you can see we're going to get minus IH bar, and then we need to take the derivative of x f of x. So here we're going to need to use the product rule, and it turns out we're not going to get the same thing. So when we take the derivative of x f of x, we take x, and then we multiply that by the derivative of f, which is again arbitrary. And then we subtract again IH bar, and then we have our function f of x times the derivative of x with respect to x, which is just 1. So we end up with this expression here. And we can come back in and see if our operators have commuted, and you can probably guess by this point that they haven't. So we can take, we use this commutator on an arbitrary function f of x, and we can say, what does this equal? Well, it equaled minus IH bar x df dx, and then minus this part here, so minus IH bar x df dx, and then minus IH bar f of x. And we can see that these two terms will cancel out, but this one will remain. And so our commutator here is IH bar f of x. And typically the way this is going to be written is with the f of x's canceled out. So we'll typically have the commutator being our momentum operator and our position operator without the f of x equals IH bar. So this IH bar is not 0, which means that our operators do not commute, and we can never know position and momentum for a quantum mechanical particle simultaneously.